Welcome back to chapter 18. In this chapter, we're going to be looking at confidence intervals for proportions. And in that, we're going to be looking at what confidence intervals even are. We're going to see a few different chapters that involve different confidence intervals, and they're all basically the same. Like there are some like little minor things here and there, but for the most part, they're basically the same. But the meaning behind them and what they are is the same. And so we're going to hit that in this chapter while looking at them for proportions. We did do this in Algebra 2 very briefly. It involved an activity where you had to flip a whole bunch of thumbtacks. And generally speaking, I would have you do that here too, but we're not in class right now, so that doesn't really work out. So the first thing is standard error. Now, what is standard error? Well, we in the last chapter we learned that the standard deviation of a sampling distribution for proportions is the square root of p times q divided by n. So it's the actual population proportion of success times the proportion of failure divided by the sample size, and then we square root the whole thing, which is great, except that we don't know what that population proportion is, generally speaking. If we knew that, we wouldn't need to make a confidence interval at all. And so, what do we do? Like, we're stuck, right? Nope. We just use the statistics to estimate the population proportion. So instead of p, we're going to use p hat. We're going to use whatever we get from our sample as our estimate for that population proportion. Now, is that exact? Probably not, but it should be pretty close. And that's where the whole idea of confidence intervals comes in. Like, we're not going to get that exact population proportion, um, but we should get something close. How close? We're going to see that. Um, Anyway, when we use the statistic instead of the parameter, so we use what we got from our sample instead of the thing that we don't know from the population, instead of the standard deviation, we call that the standard error. But it means the same thing. It's just with p hat instead of p, and also q hat because we don't know p, so we can't find q, so we use p hat. Q hat is just 1 minus p hat. Um, so that's what the standard error is. It's the standard deviation, except we use our statistic that we find instead of the parameter that we don't know and we're trying to estimate. So a confidence interval. Um, we have our sampling distributions. We have p hat should be centered at p, should be about p with the standard deviation, but we don't know p, so we use the standard error, which is what we just talked about. Um, by the 68, 95, 99.7 rule, we know that 68% of our samples should be um, within one standard error or standard deviation of that probability. 95% of our samples will have their proportion, their mean basically, within two standard errors or two standard deviations of that population proportion, and the 99.7 will be within three standard errors of the proportion. Well, that's great. We have our basically that says if we go with 95 for our example, we have whatever p is, and then we go out two standard deviations, and that means that 95% of all the samples we take will be in there. It means there will be some of the samples that we take which won't be in there, but 95% of them will be in there. Okay, that's nice, except we don't know p. We know p hat. So what does that say? So we can look at it from p hat's point of view. So if from p hat we go out those 2 standard deviations or 2 standard errors, we still have that 95% rule. Like it's the same distance. So if p hat is within 2 standard errors of p, that means that p is within 2 standard errors of p hat. I know it sounds basically the same. That's because it is basically the same. It's just switching it around. So if we're centered at p hat now, within 2 standard errors, 95% of the samples we take, it's going to capture P. It's going to capture that true population proportion. And so we'd call that a 95% confidence interval. We're 95% confident that the proportion is in between these two numbers. And we just go 2 standard errors away from P. Almost 2. We'll get to that in a second. So what does that mean? We have our Acme P-trap. It's guaranteed to capture P, with 95% confidence. So we have our P hat. That's the statistic. That's what we got from our sample. 2 standard errors each way. 95% of the samples that we take, P is going to be somewhere in that range. So we're 95% confident that P is between this small number and this large number. So now we can't say that P is because it might not be. We may have gotten a sample that was just all really big or all really small, and we didn't end up trapping P. But in 95% of the samples that we could have gotten, we're going to get P in this interval. So what is that confidence interval? A confidence interval is a method of estimating the parameter, in this case, the proportion P. In a future chapter, we'll be estimating the population mean as well. So we're estimating that parameter about the population as a whole. And so we use the sample statistic to estimate the population parameter. There it is. But since the samples do change from sample to sample, sometimes it'll be above, sometimes it'll be below, sometimes it'll be close, sometimes it won't be close. The confidence intervals that we make also will change. If the population parameter is, let's say it's a 0.6, and we have a standard error of 0.1, that means we could be at, say, we could get 4.5. 2 would take us up to 6.5 and down to 2.5. We could also be at 0.7. So there we'd go from 0.5 to 0.9 for our confidence interval. So each sample will have a different confidence interval, but in 95% of those samples, it's going to include this 0.6. And I was about to say, we're going to see a visual of that here. So here we have 20 samples and their confidence intervals. Some of the confidence intervals don't actually catch that true proportion, but most of them do. When we flipped our thumbtacks, we had a number line on the board, and you made your confidence intervals going up like that. And then we had that true population proportion. We also did it flipping a coin and getting heads, and then we flipped thumbtacks. So we had like a couple days in a row of doing this. And so 95% of them, we're going to capture that, which means 5% we're not, but we can't do anything about that. So the confidence is actually in the process of constructing the interval, not in the actual interval itself. Like, the interval might be good, it might be bad. We don't know. But again, with what we did, 95% of the time, because 95% of the intervals that we could get are going to include that proportion. Um, so we expect 95% of all 95% confidence intervals to contain the true parameter. Um, so now we have a margin of error as well. And the margin of error is that distance, that those two standard errors away from the center, away from that proportion, the p hat. Now it doesn't have to be 2, by the way. We can change the confidence level, and we'll talk about that in a second. But this is the margin of error. It's a confidence interval, and this is not just for proportions, but a confidence interval is the estimate, a proportion, a mean, plus or minus the margin of error. And that margin of error, we're going to get a more detailed formula for that in a second. So now, the more confident we want to be, the larger our margin of error needs to be. Like, I am 100% confident that the true population proportion will be between 0 and 1. That is a true statement. I am that confident, but it's a true statement, but it's a meaningless statement. Because yes, the proportion is going to be between 0 and 1. That doesn't help us at all. And so we can raise our confidence, but that raises the interval. We could get a really small interval, like I am 35% confident that the proportion is going to be between 0.6 and 0.62. It's a nice small interval, but if I'm only 35% confident, again, it's fairly meaningless. Like, there's so much chance that it's not going to be in that interval. And so getting that certainty versus precision, and there are ways of increasing the precision without lowering the certainty too much. But in general, the more certain you are, the less precise it's going to be. And the more precise, the less certain. So we could go to, like, I went all the way up to 100% confidence. Here we only go to 99.7% confidence, which is 3 standard deviations or 3 standard errors away from that proportion, that p hat. And so if our standard error was 0.1 and say p hat was 0.5, well, going 3 away, that means, hey, we're 99.7% confident that it's somewhere between 0.2 and 0.8. Yeah, but that's a really big range. So we're more confident, but we increase the range, so it's way less precise and doesn't give us as much information. So it's a delicate balance there. So to be more confident, we wind up less precise. Yep, it's a balance between that certainty and precision. And I love the tension between certainty and precision is always there. It's so dramatic. But we can do both. And that 95% confidence level is generally a pretty confident with a decent precision. It's a good balance for most things. But we do use more. Sometimes we'll use 90. Sometimes we'll use 99. 95 is just kind of the industry standard. It's like it's the most common. There are times when we do want to be more precise, um, but again, 95, it's just kind of the go-to. Um, and it is arbitrary for the most part. And those are the most common, but we could use any percent if we wanted to. And oh, we'll find that in a second. I thought we were finding that now. So our critical values. The 2 in that 2 standard deviations comes from that 68, 95, 99.7 rule. Now, that is an estimating rule. That is not actually precise. In fact, 95% isn't 2. 95% is 1.96. It's close enough to 2 for the estimate, but it's 1.96. And these are z values. So it's 1.96 standard deviations away from the mean. So we do like to be a bit more precise than just 2. And we can use a table or technology to find it. Technology, you can use StatCrunch to do an inverse normal. You can use your calculator to do an inverse normal. The table, I'm going to show you the table on the next slide, I believe, perhaps the slide after that. But that 1.96 we call the critical value, and the symbol it gets is Z star. That's what this is. Z star. We've had Z scores. This is a Z star. The difference is fairly minimal because the numbers have the same meaning. The Z score, though, we get based off the data, and then it takes us to a probability. The Z star, we choose. We are choosing what confidence level we want, and that gets us a specific critical value, a specific Z star. So the numbers mean the same thing. It's just, does it come from the data, or is it something that we're picking? So that's a Z star. And so for any confidence level, we can find the corresponding critical value, which is the number of standard errors that corresponds to the confidence level. There are a couple different ways of doing it. One is you can look on table A, the Z table, the table that we've used already, because that's where these values are. You can look on table A. Now the trick is, if we wanted a 95% confidence level, that means that there's 5% outside of it, which is 2.5% on either side. So we would have to look not for 95 in the table, we'd have to look for 97.5 or 0.975 in that table to find it. If you go to the next table in pretty much anything, the next table in the book, I believe, is this table. The next table in the AP formula sheet is this table. In the AP sheet, this is called table B. It's also the T table. It's the T distribution of critical values. This is taken directly from the AP formula sheet. I found it on one page. The one I gave to you guys had it split between 2 pages, which is weird, but it's the T distribution table. Now, most of this table we're not touching yet. We will use this here pretty soon, but right now we don't necessarily know what all of this stuff means. We're going to focus on this bottom row. So if I just enlarge that bottom row there, we have infinity. Sometimes instead of infinity, this is labeled Z star. There's those values. And then right below it's the confidence level. We want a 95% confidence level. That's the 1.96. If we wanted a 99% confidence level, we'd have to go 2.576. standard errors from the mean. If we want a 90%, we have 1.645. Generally speaking, you wouldn't use those lower ones, but these are the big ones. So just right at the bottom of that T table, in that row labeled infinity or Z star, it'll be the bottom row right above the confidence levels. We can find them super easily. Now, if you wanted a 75% confidence level, that's not here. You'd have to look at the Z table for that. So if we wanted that 90% confidence interval, as I mentioned, instead of going 1.96 away from the mean, we would go 1.645 in either direction. And that's 1.645 standard errors. And that'll get us that 90% confidence interval. Assumptions and conditions. We always have assumptions and conditions. We've had them for a number of chapters now. We're going to continue to have them. They're all a bit different, but they're all also mostly the same. And if the assumptions are not actually true, the model will be not true and the conclusions will probably be wrong. And we try to avoid that. And a lot of times we cannot guarantee that the assumption is true, but we can check to see if it's plausible. Like, does it make sense that it's true? Is it not obviously not true? Not obviously not true. Yeah. And so we can just logic our way through it, generally speaking. So the assumptions and conditions, we have the independent assumption, which we can't see that from the data. We have to see that from how was the data collected. And so for that, we have the conditions that we can check to see if it's independent. One, was it random? Was the data randomly generated? Or not the data randomly generated, was the sample randomly generated? A random number generator, was it an SRS that randomly chose people as opposed to a convenience sample or something like that? So a properly randomized experiment. We learned about that a number of chapters ago. The 10% condition is that no more than 10% of the population. Because when it gets to be more than 10% of the population, all of a sudden that whole without replacement thing starts to make a difference. The sample size assumption, because it needs to be approximately normal. Well, based on the central limit theorem that we just learned about, if the sample's large enough, it will be approximately normal, regardless of what the population is. Now, if it tells you that the population is approximately normal, then the sample size doesn't really matter that much. But if it doesn't, then it needs to be big enough when you have to have at least 10 successes and 10 failures, or expect 10 successes and 10 failures, which means that the sample has to be at least 20. And so when the conditions are met, we're ready to find the confidence interval for the population proportion. Now, notice the title here, it's not called a confidence interval anymore. The use of the term interval means it's a confidence interval. The Z interval means that we're using the Z star. That's all we know right now. But that table that we were just looking at, the T distribution, those are other values. So there will be some intervals and stuff in the near future where we'll use that. Those will be T intervals. And then we'll also have chi-squared intervals and stuff like that. But right now, we know the Z table. And so it's a Z interval. And it's a one proportion as opposed to a one sample. Like, we're dealing with a proportion, not a mean right now. And it's just one proportion. We're not comparing two proportions. So these are all things that'll happen in the next few chapters, though. Um, so the confidence interval, we have p hat plus or minus z star, our critical value, times the standard error, where the standard error is this guy right down here. Um, so and the critical value z star depends on the particular confidence that we specify. So for example, if we have p hat was 0.4 and our sample size was 30, then, and we wanted we're gonna go with a 95% confidence interval, we would have our standard error would be the square root of 0.4 times 0.6 over 30, and 0.4 times 0.6 divided by 30 is 0.008, and then the square root of that number is so the standard error is 0.089. So our confidence interval, we're going to have 0.4 plus or minus 95% gives us a z-star of 1.96. Being that 95% is so common, that 1.96 is something that you're probably not going to want to look up every single time. So we have 1.96 times 0.089. And so this would be 0.4 plus or minus 0.175. Sometimes we leave it like that. That tells us our p-hat, it tells us our margin of error. But specifically, it tells us the p-hat. But sometimes we'll actually put it into an interval. So 0.4 minus 1.75, or 0.175, is 0.225. And 0.4 plus 0.175 is 0.575. Now, that's a great interval. That would not be the answer, though. The answer needs to be in context. The answer would be in the form of a sentence. It would include the confidence level. So if we were estimating the proportion of people that like or that eat tacos on Thursdays, because why would you eat tacos on Thursdays? Or a better question, why wouldn't you eat tacos on Thursdays? I am 95% confident that the proportion of people that eat tacos on Thursdays is between 0.225 and 0.575. That would be the answer. You can read, or you can see it. It tells you what you're talking about. It gives you the confidence level. I am 95% confident. I am 95% certain that the people who eat tacos on Thursday, or the proportion of people who eat tacos on Thursday, is between these two numbers. Or I'm 95% confident that the proportion of people who eat tacos on Thursdays is in the interval 0.4 plus or minus 0.175. That 0.175, that margin of error, by the way, is what we see in like studies and papers where it's like, it has a margin of error of 3%. That'd be 0.03. So it's that plus or minus 0.03. It's a confidence interval. They generally just give the p-hat as the actual value, because otherwise it gets kind of confusing, especially for people that don't understand statistics, but that's what it is. So choosing your sample size. We saw in that last one, we had a margin of error that was really big. It was like 17.5%. That's a big swing one way in like each direction from that proportion. So how could we shorten that margin of error? Well, we could drop the confidence. We could lower, instead of 95% confident, we could be 90% or 60% confident. That would lower that. But we don't want to do that. We like to be more confident. We like that 95% confidence. So um, the question is, what else could we do? The margin of error is z-score. We can change that by changing the confidence. We have p-hat and q-hat, which is directly related to p-hat. We can't really change that. That's the proportion we're trying to estimate. But beyond that, we don't even usually know that before we take the sample. And so we have the n, the sample size, is something we can use to adjust that. We adjust that margin of error. So um, we can choose the margin of error, we can choose a confidence level, and then we can figure out what sample size we need. Now, since we don't usually know what p-hat or p is going to be, if we have prior information, we could take a best guess. Or use 0.5, because if you use 0.5, that will give you the largest sample size possible. So it doesn't matter what that proportion is, the sample size will cover it. Maybe your margin of error isn't 3% now, maybe it's actually only 2.7%, but having a smaller margin of error is even better. So to do this, we had a 17.5% confidence or margin of error in that last problem we did. Well, how could we shorten that? Getting a bigger sample instead of 30 people. Let's choose another one. Let's say we want a margin of error of 10%. So we're going to go 0.1 equals, that 1.96 isn't going to change, square root. Now we knew it was 0.4 because that was after we already took the sample. But before we take the sample, we're just going to say it's 0.5 times 0.5 over n. Now we're going to solve for n. So the first thing we would divide by that 1.96. So 0.1 divided by 1.96 is going to be 0.051. With some extra decimals there. I'm using the values in the calculator. I'm only actually writing down a couple places though. Is going to equal square root of 0.5 times 0.5 will be 0.25 over n. So now we need to square both sides. So that 0.05 squared is now 0.0026 equals 0.25 over n. And now we can multiply by the n and divide by that 0.0026. So n would be 0.25 divided by that number, which would give us 96.04000 something. So 96.04. Now, generally speaking, that would round down. But if you round down and your proportion does actually happen to be 0.5, your margin of error is not going to be 0.1. It's going to be like 0.1001. Like it's going to be bigger than 10%. And so when you find your n, you always round up. So we're going to use n equals 97. You always round up for your n. So that's how you can figure out your sample size, the sample size you need for your population, or for your sample, before you ever find your sample. And that'll get you the margin of error that you want to have. So what can go wrong doing confidence intervals? Generally speaking, people find confidence intervals fairly accurately. Oh, you can do them in your calculator too. Um, if you go to stat and then to calc, nope, tests, there's all the intervals. We have one prop z test. That's what we're doing right now. And then it has you plug in. You can do it with data. You can do it with your statistics. It's a fairly easy process, but I can help you through it if you need it as well. So finding the confidence intervals is generally not the problem. The problem is, well, one, not putting it in context, like writing a sentence as your answer. That's a big one. Um, but other ones that are big, don't suggest the parameter varies. How would you do that? 95% of the time, the parameter is going to be in this interval. Wrong. The parameter is either going to be in your interval or it's not going to be in your interval. 95% of the intervals you could find will include the parameter. It's subtle, but the parameter will either be in your interval or it won't. That's why when you have your sentence, I am 95% confident that the parameter will be in this interval. Not 95% of the time it will be. I am 95% confident that it will be. Don't claim that other samples will agree with yours. 95% of the time we're going to get a p-hat that looks like this. No, it's not about other samples. You're trying to estimate the population parameter. Other samples are all going to be a bit different. Don't be certain about the parameter. P-hats in between here. You have to include that confidence level. I'm 95% certain that p-hat's going to be in between here. Don't forget it's about the parameter, not the statistic. We are estimating that population value that we don't know. We know everything we want to know about our sample. Don't claim to know too much. That comes in a variety of ways, but you know just what you know. You know what the problem tells you. Don't don't overdo it. I know one of the cardinal sins on the AP test is not shutting up, because nobody cares how smart you are. They care about how you know stuff. If you have a problem about whales and you're studying to be a whale biologist and you know more information than the problem gives you, keep it to yourself. Write a book about it later. Leave it out of the problem. It's just about the data you have in front of you. Do take responsibility for the uncertainty. I'm 95% confident that it'll be here. It might not be here. I mean, I'm 5% confident that it won't be in the interval, but that's part about don't be certain about the parameter. It's kind of the same idea. And then do treat the whole interval equally. The population proportion is no more likely to be in the center as it is on the very edges. We just are 95% confident that it will be somewhere in the interval. The interval we had before went from 0.225 to 0.575. 50%, 0.5 was in the interval. So we don't even know if less than half the people or more than half the people eat tacos on Thursdays, because 0.5 was included in the interval. Yes, it was way on one end of the interval, but that doesn't matter. It was included. The margin of error is too large to be useful. So, I mean, can't be exact. That's that tension between the precision and the confidence. We can make the margin of error smaller, is to reduce our confidence, which is not generally good. Think about the margin of error when we design it. So to get a narrower interval, we need a bigger sample. Um, Now that we went from what we did to go from 17% or 17.5% to 10%, we had to increase our sample from 30 to 97. So I mean that was more than 3 times. If we wanted even smaller samples, like or even smaller margin of error, that sample size is going to increase a ton. So I mean there's a little bit of give and take there as well. Um, and so we choose our sample size, always round up from whatever that number is, um, and then show your rounding as part of your work. I had n equals 96.0 something. So we're going to use n equals 97. I showed that I rounded up. Um, Other things that can go wrong, look for the violations of assumptions. Bias sampling. That was chapter 11 when we learned about sampling. And you have to get that based on how the sample was taken. And then be thinking about the independence. Does it make sense that the samples are independent based on how it was taken? So what have we learned? We learned to construct a confidence interval for proportion. It's p hat plus or minus the margin of error, and the margin of error has that critical value, the z star, based on the confidence level that we want, and we can find that in the table. And the standard error, which is basically the standard deviation, except we use the sample statistic that we know as opposed to the population parameter that we don't know. And it's p hat plus or minus the z star times the standard error. We've learned to interpret confidence intervals. You can claim to have a specified level of confidence that the interval you have computed actually covers the true value. Again, I am 95% confident that the population proportion is in this interval. Um, Understand the relationship of sample size to both the certainty and the precision. For the same sample size and true population proportion, more certainty means less precision. So that's I'm 100% confident that it's between 0 and 1. I'm very certain, but there's no precision there. Um, and then more precision implies less certainty. That's where I'm 35% confident that it's in this little interval. We've learned to check assumptions. It needs to be the independence or randomization, the 10% condition, and the success failure. So no more than 10% of the population. And then we need at least 10 successes and 10 failures, so that we have a sample size big enough that the central limit theorem kicks in to make sure that we have a normal population. Unless it says that it's an approximately normal population. Sometimes it will, then you don't need to check that. Learn to find the sample size required to get that confidence level and desired margin of error. AP tips. Don't forget to check your conditions. Always, always, always check your conditions. They are always worth points, or at the very least, sometimes like you'll check for the you'll check your to see if the central limit theorem kicks in. Well, it already said that it was a normal population, so you didn't have to do that, but they're not going to mark you down for that. But if you didn't check it and it didn't tell you, then you start losing points. When you're doing a confidence interval question on the AP test as a free response question, there are 4 parts to it. One part is check your conditions. One part is do the right tester interval, either by name or by formula. One part is the mechanics, actually finding the interval, and one part is the conclusion in context. So we have conditions, we have the test, the procedure, test or interval, And that could be, we're doing a one proportion z interval, or it could be p hat equal plus or minus z star times the standard error, or times p hat 1 minus p hat over n. So either of those would give you that tester interval point. Then doing the actual interval, you don't actually need work doing that. So we have this, the interval is going to be 0.225 to 5.75. And I know a lot of times, in math, we're like, wait, but we have to show our work to get there. No, that is the work. The answer is that sentence in context. So we have the test, we have the interval, then we have the mechanics, which is where we actually find the interval, and then conclusion in context. These are the 4 points. Each of these are going to be essentially correct, partially correct, or incorrect. And then the question's worth 4 points. Partials are worth half a point. Essentially corrects are worth a point, and incorrects are worth nothing. You can just basically add up your points. If you don't check the conditions, you could lose a half a point or a point off of the 4-point problem. It's a big thing. And then be prepared to interpret the confidence level as a follow-up question to interpreting the interval. Sometimes it breaks it up into part A and B. Sometimes it just says find a confidence interval, or estimate the proportion, the population proportion. And so you do the confidence interval. But those 4 things are there. You can number them 1, 2, 3, 4 too when you're doing this. I've seen AP tests that it's just numbered. 1, check conditions, and then they check their conditions. 2, identify the procedure. It's a 1 proportion z interval. 3, mechanics. This is the interval. 4, conclusion. I'm 95% confident that blah, blah, blah. So, AP tips. This is the start of a bunch of chapters that are all going to be working on about the same thing. So it might not make perfect sense right now, but we're going to keep coming back to these confidence intervals over and over and over again, and tests which are almost identical over and over and over again. So don't lose hope. But I will see you in class. Until then, keep working problems, keep asking questions, and as always, happy mathing.